icon. So it's kind of interesting because instead of writing code, do something or something or anything, you just have kind of icons. You have little pictures of things and you draw wires between them. And it's a programming language, but it's really useful for programming computers to control experiments, both to control equipment and to collect data, and then to analyze and display data. So it is a language that was developed by National Instruments, this big company, and it's become a kind of an industry standard. Pretty much everybody now uses LabVIEW. So typically you would buy a card for your computer or an external unit with a USB plug-in. You connect it either put in the card or connect the USB guy, and then you run some kind of connection from the card or the USB device to a piece of equipment. For example, to a voltmeter. You can collect voltages. Or you can make a voltage. If you want to apply a voltage to something and you want the voltage to vary in time, you can program the computer to do that. So it's a really, really useful thing, and when you're doing experiments here in the Institute, you'll need to know it. Now, there is a demonstration of LabVIEW, a kind of a hands-on demonstration of LabVIEW by National Instruments that I want to schedule sometime in October, and I want to make sure that you guys are interested and you are free. And so this would be, I think, a two-hour effort, and a person would come, give a little talk, give laptops to everybody, and you guys can try to do various things, as they kind of want to do. So I think this is a good thing to do, and the tentative date for this is October 20th, which is a Tuesday. So my question is, what is your schedule on a Tuesday afternoon? Can you guys be free?
We have a call until 3:30.
You have what?
Structured fluid until 3:30.
Okay, so from 3:30 on,
That's the rest of our.
you're free. True for everybody? After 3:30, everybody's free? So maybe we'll schedule it then for
We are
3:30.
free in the morning also.
Well, that's possible too.
But they have ELM.
Everybody have calls.
Yeah. Okay. So after 3:30 it will work. And so how many of you are there now? 1, 2. Who will not go to this LabVIEW class?
Everything.
Okay. Okay. Good. All right. So basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. I think that can be done in one session. So let's please pencil this in then.
Is this just the introduction of LabVIEW?
Well, it's both a kind of an introduction and to give you a perspective on what the possibilities are. Okay, just to,
I don't need to.
no?
Actually, I can't. I have a lecture.
Really? Good. But you know the current developments, because there's new things in for example, in image analysis and motion control and things. So, okay, so you don't. Okay, so we have 13 people then. So please pencil this in for October 20th in the afternoon, and we'll try to do it starting at 3:30 after the class. Okay. Good. Okay, now pushing on. So the last big development in classical mechanics is Hamiltonian mechanics. Okay, so this again is a big step forward after Lagrangian mechanics. And here the basic idea was to have, in addition to these generalized coordinates, the q's, to define something which is called conjugate momenta. So we have generalized variables, and then in Hamiltonian mechanics, one constructs conjugate momenta. And basically the idea is that first you make the Lagrangian, which you now know how to do. You choose a Q, Q dot, have K minus U, then you have the Lagrangian. And then the conjugate momentum, Pi, to the generalized coordinate Qi is the partial of the Lagrangian with respect to Qi dot. And so the Lagrangian contains only Q's and Q dots, and so the conjugate momentum is just this. So this is the momentum conjugate to Qi. So the first thing then is to obtain the conjugate momentum. This again is just a definition really. But you can see how it kind of works. If you have, in a kinetic energy, you have 1/2 mx dot squared. If you take the derivative with respect to x dot, then you get mx dot, which is the momentum. So it kind of works. Okay, so for every conjugate variable then, you can obtain a conjugate momentum. And then the thing is that you then define a thing called the Hamiltonian. And the key notion here is that the Hamiltonian is only a function of the Qi's and the Pi's, nothing else. No Q dots, nothing else. Only Qi's and Pi's. And this is just the total energy. So this is K plus U. Once you have the Pi's, you should be able to write both K and U in terms only of Qi and Pi. Okay, but this is still just definition, you know, where is the meat? And the dynamics you get by noting that Q dot is equal to the partial of the Hamiltonian with respect to Pi, and Pi dot is minus the partial of the Hamiltonian with respect to Qi. Okay, so these are the equations of motion. And again, it turns out that using Hamiltonian mechanics, you can solve a lot of problems that you couldn't solve certainly by Newtonian mechanics, very difficult in Lagrangian mechanics, but becomes almost trivial in Hamiltonian mechanics. So this is the third step. Okay, let's see if we can, so these are the equations of motion, right? So let's see if we can make this work in a little problem. So do the example. Same as before. Spring, mass. So we need to choose a variable, Q. So we again choose X. Unless you guys want to do something else. But choose X and then you can play around with other things just to see what happens. So once we have chosen a generalized coordinate, the next step is to figure out the conjugate momentum. Okay? To do that, we have to form the Lagrangian. So we have Q, we have Q dot, we need this for the Lagrangian, and then we have the Lagrangian is 1/2 nx dot squared minus 1/2 kx squared, like before. And now we want to get the conjugate momentum. We just take the partial of the Lagrangian with respect to Q dot, with respect to x dot. So P is just the derivative of this with respect to x dot, and that is just mx dot. Okay. now we have our Q and our P. Okay, so, and this is the prescription, right? So make the Lagrangian, get the conjugate momenta, then write down the Hamiltonian. So the Hamiltonian for us is going to be the energy, kinetic energy, written in terms only of Q and P. So what would it be? How do we write the kinetic energy, this guy, in terms only of Q and P?
X dot is P by M.
Hmm?
X dot is P by M. P divided by M, X dot. X dot.
Yeah, X dot is P over M, right?
So half M
P.
X dot square is P squared by P.
Yeah, P squared by 2M, good. So this is important. We have to write the kinetic energy in terms of momentum because of X dot squared we need P squared, so we get P squared over 2M. Okay, and then the potential energy, that's in terms of Q already, so no problem there. And we are not taking the difference anymore, we are taking the total energy, the sum. So we have plus 1/2 kx squared. Now the Hamiltonian is something that you'll see a lot of. We'll be talking about the energies of various particles in various liquid crystal molecules in fields and things. The Hamiltonian is the guy that we'll be working with. So the main thing you want to remember then is that it must be written in terms only of coordinates and conjugate momenta, and the conjugate momenta are defined in this way. Okay, but now we have the Hamiltonian. We still don't have the equations of motion. So if you want to figure out what the motion is, we said that Q dot is equal to dH by dP. And so if we do that, we get Q dot is equal to P over M. Okay, so that's one of our equations of motion. That's kind of obvious, right? X dot is P over M. The seat of the gland. And the more interesting one is P dot is equal to minus dH by dQ. So now P is mx, so here we have mx double dot, right? If I take P dot, mx double dot, and that's equal to minus dH by dQ, which is this guy here, which is kx. So once again, we get the same old mx double dot plus kx. So first they all work. And this looks pretty complicated, and I agree, if our only problem was this, there wouldn't be much point in doing it. But in general, it turns out that this is a very, very powerful way of solving mechanical problems. So this is really what you need to remember in the end, is how to form the Hamiltonian in terms of Q's and P's. To do that, you have to first make the Lagrangian to make sure you have the right conjugate momentum. Because in problems that we'll do involving many angles, it won't be at all clear what the momentum corresponding to certain coordinates is. Okay? So that's all. That's kind of the end of the review of classical mechanics. The next thing we'll do is we are then going to use this notion of describing things in terms of Q's and P's to count states, to count states of systems. Yes, Sean?
I have a question about the kinetic energy here. Can we express directly as a sum over I, pi squared divided by 2m?
Often you can, but not always.
Okay.
I mean, in this case, in the simple case, you can.
Yeah, because the generalized coordinate is also the real coordinate. So it has the same, so the conjugate momentum also has the same unit as the real momentum.
Right.
So you can write it down as p squared over 2m. But if a unit of the conjugate momentum is not the same as the real momentum, you can't do that, right?
Well, there are even cases where it's not just a dimensional issue, and when we talk about rotation, so if you have an object that has two angles describing it, then you have two coordinates, say theta and phi, and you need to talk about kinetic energy associated with that rotation, then you find that it's not so simple, and you cannot simply say what you said, that the momentum associated with theta and phi, or just kind of quadratic terms that you can add.
So basically you have to write down the expression of the kinetic energy from physics.
That's right.
Instead of simply mathematics.
Sure, absolutely, yeah. That's exactly right. And then the thing is, once you have the kinetic energy, you must express it in terms of Q's and P's. And you can always do it. Okay, so is everybody happy with this? So this seems a little abstract maybe, but it will become real soon enough. And we'll be using this Hamiltonian formalism for two things. First, to be able to count states, and second, when we'll be making free energy, that'll be a Boltzmann factor that you're familiar with. In the Boltzmann factor, what goes in there is the Hamiltonian. So that's why we need the Hamiltonian. It's not enough to write the total energy. It has to be in Hamiltonian form so that we can really do the sum over states correct. Okay, so that's it. And now I'll hand out the notes. I'll hand out half of each hand. I don't know what the outcome of that distribution. And I think I'm happy to stop here today because, I mean, sort of conceptually it finishes this story. And the next thing we'll talk about is probability. Maybe this is a good time to talk about probability a little bit. We have a couple of minutes here. So first of all, any questions on this classical mechanics stuff? Like I said, it's pretty simple, but it's important that you understand it well. And like I said, a good practice thing is to don't choose X for the simple problem as your coordinate. Choose something else. See how things work out. Good exercise. Okay. So let's talk about probability. We have to talk about probability because ultimately, when we look at complex systems, all we can do is argue that the most probable result of a measurement is some. You have a gas and you measure the pressure. You're not really sure what the pressure is because you have all these particles hitting some membrane, and you could have more particles, less particles. So all you can say is that on the average, this is what happens, or the most probable thing is this. So we have to talk about probabilities, and probability theory can be kind of tricky, and I know when I was a student I didn't like it much because there were all these examples that were sort of counterintuitive. But I think a simple notion of probability is just to think of it in terms of fraction of outcomes. The probability that something happens half of the time means that half of the outcomes, if you do the experiment long enough, will be this, the other half will be that. If I flip a coin, if I flip it once, it can be heads or tails. But if I flip it, say, 1,000 times, then I'll find that pretty close to 500 will be heads and 500 will be tails, if it's a true coin. And the more I do it, the less the scattered in the results will be. So I think probability, a nice way to think of it is the probability of something happening is just a fraction of the time that the outcome is that instead of something else. Okay? It's pretty simple. Everybody happy with this? So, you know, if I want to know what is the probability that a Kent State student chosen at random is, I don't know, 5 feet tall, then what does that mean? Well, first of all, exactly 5 feet is a kind of a funny question. Usually, I would measure this person somehow, and my measuring instrument.
I have a question. I didn't hear the probability of what?
Oh, what is the probability that a student chosen randomly from Kent State University is 5 feet tall?
0.
Okay, so, yeah, so first of all, to say that it's exactly 5 feet tall is 0, right? But the probability that his or her height is in some interval, say, you know, 5 feet and 5 foot 1 inches, is not 0.
It depends on how we measure it. If we can measure only 4.9 feet, then we can measure 5 feet, and then we can measure 5.1 feet.
Right.
And it's
But okay, so well, let's suppose that we have a meter stick with 1 inch, with a meter stick, and, you know, certain accuracy, delta x, and then we ask what is the probability that a randomly chosen student has height of 5 feet, you know, plus or minus half of this accuracy interval. And the way, you know, you would do that would be to measure the heights of all the Kent State students, right? And see how many fall into this window, and then the probability would be that number divided by the total. Right? So that would be a good operational definition of the probability of that event. And I think that's a useful way of thinking about it, because it gives you kind of a practical way of actually measuring it, if you could get all the students, you know, to stand while you measure the time. Okay, so now I want to talk about this problem that maybe illustrates the usefulness of looking at probability this way. And this is a kind of a famous problem, and maybe you've heard about it. But this was a hypothetical problem posed by somebody in a magazine, and then everybody was asked to provide their answer, and many professors of mathematics provided the wrong answer. Interesting problem from that point of view. And the problem is this: so there's a television show, television game show, and it's called the Monty Hall problem. It's a television game show, and this guy, Monty Hall, is the host of the show. And the show goes like this. There are 3 doors. And you are the contestant, Sean, you're the contestant. I am Monty Hall. And I say to you, Sean, behind one of these doors, there's $1 million. If you guess correctly where the $1 million is, it is yours. Okay? So guess where it is.
The first one.
The first one. Okay, so Sean guesses this door. Now, I open another door. I open this door. I open it. And I say, look, Sean, there's no money here. And it doesn't matter where the money is, I can always do this, right? If the money is here, then I open this door. So I open a door and I say, look, Sean, there's no money here. And then I say, do you want to change your choice now that you know that the money is not there? Or do you want to stay where you are? And that's the question. To maximize the likelihood of you winning, should you change the door that you have chosen or not? Change. Why?
Actually, I didn't know why, I just see
Okay, that's a good reason. Move it to the right.
Well, we can count it somehow.
Well, that's what I would like you to do. I would like you to think about this problem and figure it out.
Okay.
So, and
But we should change, I think. If I'm not mistaken, I've met this problem somewhere, and it really happens so that the probability to win that million is more if you change your decision.
right.
And it somehow it is connected with it's probably conditional probability, right? Or the probability after something has happened.
But don't complicate it. You know, there's all these people talk about Bayesian statistics, and you can make this very complicated. It's not a really complicated problem. But I think if you think in terms of counting outcomes, you can understand it clearly. It's an interesting problem because it turns out that you should change. I mean, as you know from movies and other resources. But it's interesting because many professors wrote and said, you don't change, it makes no difference. That's what they said, it makes no difference. The probability of it being here or somewhere else cannot be altered by the fact that you opened the door. It cannot possibly change, and I will give up my tenure if I'm wrong.
I have one, suggestion how to explain it. Let's say we have, this is the same as we have to change 2 chances to win the million, right? The first one and the second.
Well, we have one chance to win a million.
No, but we made 2 decisions.
You can either stay at this door or go to the other.
Yeah. The first decision has a probability of 30%, 33. The second is of 50. And nothing would change if we didn't open that door and then change our decision once more, right? So if I choose first one door, then I change my mind and choose the other door. Still, the probability would be 30%.
Okay, so I want to quit here now because the time is up. But I'd like you guys to think about this problem. It's an interesting problem. And I think a nice way to do it is just to do an experiment. Do an experiment. Either get a friend and you do it a few times, or write a computer program which will do it for you. It'll put the thing behind one of the doors and open a door randomly.
There's one thing missing for us. We don't have a million.
Yeah. Well, I don't either. Okay. So we'll see you guys on Friday.